Hello everyone and welcome. My name is Jason Gregerson. This video is going to be a walkthrough of the Practice Exam 1 for linear algebra. So I'm just going to talk through my solutions as this key. The video is not intended to be something that you would just watch straight through. Rather, the suggested approach is that you go through the blank exam, you grade yourself according to the key, and you reference the video if you have specific questions about specific problems. Alright, so let's go ahead and get started. So we have a bunch of matrices and a bunch of questions about those matrices. The first one is looking for the 2, 3 position. So this is second row, third column, right? So that'll be a value of 4. So this guy would be 4. So once again, the idea here is we got rows and we got columns. Okay, the next one is the B2, 3, so second row, third column. There is no third column of B, so this guy is NA. There is no B sub 2, 3. Next we have what is A plus B. So when we add matrices together, we can only add matrices of the same dimensions. So here I have a 3 by 3 matrix A and a 3 by 2 matrix B. So I cannot add those two matrices together. What about 2b minus c? Well, b and c are the same size, so if I take my matrix B and I multiply it by 2, that's just multiplying all the components by 2. So if I multiply all the components by 2, I would get this. And if I subtract the matrix C, which is this matrix, I just subtract them component-wise. So I'll have 0 minus 1 in the first component here. I'll have negative 6 minus 2, negative 2 minus 0, 2 minus negative 1, so that's 2 plus 1. And then 2 minus 1 is 1, and 0 minus 3 is negative 3. So this should be 2b minus c. Next I have what is D inverse, where here's my matrix D. So if we zoom out so we can see that, to calculate the inverse of a 2 by 2 matrix, if I have a matrix that is A, B, C, D, that's my matrix A, then the inverse, the formula for a 2 by 2, is 1 over AD minus BC times the matrix I get when I switch the values on the strong diagonal and change the signs on the off diagonal. So in my specific example, if D is 4, negative 3, negative 2, 2, then D inverse be 1 over this product, 8, minus this product, a lot of minus sign here, so negative 3 times negative 2 is positive 6, and it's minus that value, so I'll have minus positive 6, times the matrix I get when I switch the values on the strong diagonal and change the signs on the off diagonal. I could certainly leave it like that, or I can clean it up a little bit. 8 minus 6 is 2, so if I multiply through by 1/2, I'll get 1, 3 halves, 1 and 2. This would be my inverse. I can always check that by just taking D inverse times D, and hopefully I'll get to the identity matrix. So that would be my check if I wanted to when I'm all done. All right, back up to the top here. What are the dimensions of B? What is the dimensions of B? Probably should phrase that. What are the dimensions of B? In this case, it's a 3 by 2 matrix, rows and columns. What is the dimension of A times B? Well, if A is a 3 by 3, and I'm multiplying it by a 3 by 2, I can do the multiplication because I have those inside numbers matching, right? The columns of A, the number of columns of A, match the number of rows of B. And the outside values will give me the dimension of the product. So the product matrix AB is going to be a 3 by 2 matrix. Next is what about AC? What is AC? Now this is not asking for the dimension, this is asking for the actual product. So now I have to take my matrix A, 1, 0, 2, negative 1, 1, 4, 3, 0, 2, multiply it by my matrix C. When I'm doing this multiplication, I'm going to do the row vector method. I'm basically taking the matrix times the first column to get the first column of the product. And to multiply the matrix by the first column, I take that row, basically dot product, times that first column, where I'm multiplying each component by each other and adding them up. So it's 1 times 1 plus 0 times 0 plus 1 times 2. I'll get a value of 3 up here. And then after that, I just kind of keep going down. Right, so now I'll look at the second row times that first column. I'll get negative 1 plus 0 plus 4. That looks like 3. Keep going down. I will get 3 plus 0 plus 2. That guy will be 5. The action of multiplying by the first column, because that first column is 1, 0, 1, basically tells me to add the first and second columns of A together to generate this column. All right, so we've done that. Now we move on to find the second column of the product by taking A times the second column of C. This time I'll get 2 plus 6 is 8. I'll get negative 2. I'll get negative 2 minus 1 plus 12. So that guy is going to be 9, positive 9. And then I will get 6 plus 0 plus 6. So it's like I got 12 down here. So that looks to be my result. A times C. Next, what is A times D? Well, A is a 3 by 3 matrix. D is a 2 by 2 matrix. I can't do that multiplication. So this one's going to be NA because I can't do the multiplication. Next, what is B transpose? Well, to take the transpose, I'm just switching the rows and columns. So in this case, I have a 3 by 2 matrix B. That means the transpose is going to be a 2 by 3. I'm basically going to take the first column of B, 0, negative 1, 1, and make it the first row of the transpose. I'll make the second column the second row. Right? So I take the value here, right? This is the value in the 2, 1 position, and I move it here to the 1, 2 position. That's what we mean to take the transpose. So there is my transpose value. Clean up a little my scratch work here. Erase some of my random lines. All right, that really wraps up the first page. Moving on to the second page. Question 2 says label each of the augmented matrices below as either row echelon form REF or reduced row echelon form RREF or neither. So really here I'm looking at first, I have identified my pivots here. So I have those values, I have zeros below those pivots, so I'm in REF form. However, the pivots are not equal to 1 and there are not zeros above the pivots, so it's not RREF, but this is in REF form. Next one, I have a pivot here, I got a pivot here. Those are both 1. I have zeros below those pivots, I have zeros above those pivots. I've moved any rows of all zeros to the bottom. This guy looks like it's an RREF form. Next is for each of the row augmented matrices below, row reduced augmented matrix below, circle the pivot positions, and then state which of the following best describes the solution set. Single point, a line in R3, a plane in R3, or no solutions. So first I'm going to identify the pivots. Even though that guy is in the far right column, that's still considered a pivot. There is a pivot in the far right column. So those are my pivots. Because there's a pivot in the far right column, this last row pretty much gives me the equation that looks like this. And that can never happen. So in this case, there's no solution. Now note, even though there is a free variable, x3 is a free variable, there's still no solution. Now I look at the next one. The next one, I only have one pivot here. There is no pivot in the far right column, so there are solutions. The question is how many, right? I see that x2 is free. Oops. I see that x2 is free, and it looks like x3 is also free. That tells me there's infinitely many solutions, but is it going to be a line or a plane? Both of those have infinitely many points on them. In this case, because there's two free variables, so because there's two free variables, right, solutions are a plane in R3. If there was one free variable, then it would have a line in R3. Moving on to the next one, I have a pivot here, I have a pivot here, I have a pivot here. There is no pivot in the far right column, no pivot over here, so there are solutions, but there are also no free variables, right? So no free variables. So let's say this guy is consistent because there's no pivot in the far right column and there are no free variables. This implies one solution, which is a point in this case in R3. Right, so the solution is x1 is 0, x2 is 0, x3 is 0. It's the origin in R3. All right, now we got true and false. A system with free variables is always consistent. A system with free variables is always consistent. This is false, right? So an example actually would be right up here in 3a that has free variables, but there are no solutions. Consistent means that there are solutions. Next, the augmented matrix has a solution if and only if B is in the span. This one is true. B is in the span means that B is a linear combination of those other vectors. That means that there is some x1, some number, where x1 plus this guy plus x2 times this guy is equal to B. There is a solution to the vector equation. That's what it means for B to be in the span. How would I solve that vector equation? I would augment the matrix and do the row reduction. So it's basically saying if there's a solution to the system, only if there is a solution to the system. Right? So this guy's going to be true. Part C, elementary row operations can change the solution set of a system. That is false. That is false. So the idea is that we have our augmented matrix and we do our row operations to some nice form, and so then we can write out our solutions. And the whole idea is that those are the same solutions for our original system. So row operations don't change the solution set of systems. Next, if a matrix has a pivot position for every row being the keyword here, then the associated linear transformation is onto. So the idea is if we have a pivot in every row, it doesn't matter what we augment with, there will always be at least one solution. So a pivot in every row means at least one solution, and we associate that with the transformation being onto. So this is true. Right? Onto means that for every B in the codomain, there's at least one X that maps to it. Right? There could be more that map to a particular one, but there's at least one. Always a solution. So this one is true. E, given an m by n matrix A, if m is less than n, then A must have linearly dependent columns. Right? So this can be tricky trying to memorize this with m's and n's, so I like to give myself an example. Right? So if I'm looking for an example where m is less than n, right? So if I said A is a 2 by 3 matrix, well then I'll just kind of write that guy out. That means 2 rows and 3 columns. So there's my matrix A. And then it's talking about linearly dependent columns versus independent columns. Well, I know that the columns are independent if there's a pivot in every column. But if my matrix is 2 by 3, at most I could have 2 pivots, which means there can't possibly be a pivot in every column. That tells me that this matrix has to have linearly dependent columns. So, given an m by n matrix A, if m is less than n, then A must have linearly dependent columns. That appears to be true. Next one, a set of 4 vectors in R3 must be linearly dependent. This is very similar to the previous question. So if I wanted to take 4 vectors in R3 and determine if they were independent or dependent, what I would do is put them into a matrix and do row reduction and see if there's a pivot in every column. But the vectors are in R3, which means each one has 3 components, and we have 4 of them. So the matrix I generate to test dependence would be a 3 by 4 matrix, right? And so if I look at the previous example here, because m is less than n, this guy has to have linearly dependent vectors. So any set of 4 vectors in R3 must be linearly dependent. True statement. So this is an example of 2 different ways to essentially ask the same kind of thing in a true or false. So be aware that many of these questions could be rephrased multiple ways. Continuing on, there is a unique basis for every vector space, a unique basis, one and only basis for every vector space. Well, if you think about a vector space like R2, for example, one example of a basis would be this. Right, my standard basis, my favorite basis here. Those 2 vectors are linearly independent, and I can build the entire space with them. These 2 vectors span the space and are linearly independent. That's what it takes to be a basis. But another example might be this, 1, 0, and 1, 1. These 2 vectors are also linearly independent, and they also span the entire space of R2. So both of these would be a valid basis for R2. So there are infinitely many choices for a basis. They will all have two vectors in them, but they're certainly not unique. So this is false. There is not a unique basis for a vector space. Next, if A is invertible, then the dimension of the null space is equal to n. Right? So here we want to think about the different definitions of these little pieces. So the null space are the solutions to AX equals 0. Are the solutions A equals 0. So if we thought about what a solution to this might look like, we might have some real problem and we would solve it, and let's say there was two free variables, then our solution would look like this, x2, x3. And in that case, we'd have two vectors in the basis for the null space. So we have a basis vector for every free variable for our null space. So the dimension of the null space can be determined by finding the number of free variables. Okay? So if the dimension of the null space is equal to the number of free variables, in other words, the number of columns with no pivots, and the dimension of the null space was n, that would mean is that none of the columns would have pivots, but to be invertible, there has to be a pivot in every row and every column. So this would definitely be false. It turns out if this was the dimension of the column space, the dimension of the column space was n, then A would have to be invertible. So the problem here is its dimension of the null space, not column space. Last one in the true and false, if V is a subspace of R3, then 0 must be in V. And there's basically three different criteria for a set of vectors to be a subspace. To be a subspace, we have to have three conditions that are met. It must be closed under vector addition. It must be closed under scalar multiplication. And it must contain the 0 vector. So 0 must be in that set for V to be a subspace. It's just one of our three criteria. So this guy is true. Next we have fill in the blank. And this is really just kind of a test of the vocabulary. So we'll just read through these essentially. The set of all linear combinations of a set of vectors is called the span of the set. That's the definition of span. If a matrix have a pivot position in every what, then the associated linear transformation is onto. We talked about this in true and false. If there's a pivot position in every row. Remember, onto says that for every B, there's at least one X. There's at least one solution to AX equals 0. And if there's a pivot in every row, pivot in every pivot, 0, 0, pivot, some number, if there's a pivot in every row of A, there's no way there could be a pivot in the augmented column. That tells me there will always be a solution. C, the matrix equation in the form AX equals 0 is called homogeneous. It's a homogeneous matrix equation. Homogeneous. This equation is always consistent. Consistent because X equals 0 is always a solution. So a system is consistent if there is a solution. This solution is called the trivial solution. Right? The 0 solution to the homogeneous equation is called the trivial solution. D, for a set of vectors to be a basis for a space, they must span the space and be linearly independent. Those are the two criteria for a basis. E, the set of all solutions to the homogeneous equation AX equals 0 is called the null space. The null space of the matrix A. That's the definition of null space. The rank of A is the dimension of the column space of A, the column space. The number of vectors in the basis of a vector space is called the dimension of the space. And that's a word to be careful with. We talk about the dimensions of a matrix. which are totally separate from the dimension of a vector space. Totally separate from the dimension of a house, by the way. Right? So dimension can mean different things in different contexts. In this context, the dimension of a vector space is the number of vectors in its basis. All right, that concludes the fill in the blank. Now we go on to some more problem solving here. So this says find the solution of the following system of linear equations and express the solution in parametric vector form or state no solution. And then we break this down into subparts. The first one is write the augmented matrix for the system. So I'm simply going to pull the coefficients here. First equation tells me 1, 2, 0 for x3, augmented with 3 on the right hand side. And I will just do that for these other values here. Writing out the augmented matrix. Then I need to do the row reduction. All right, so I'm going to do a couple row operations here to save myself a little space. I'm going to say row 2 is equal to row 2 plus row 1. So I'm going to take the second row. I'm going to add the first row to it. So first row is going to stay exactly the same. Second row is going to become 0, 0, 0, and 0. I'm going to do another row operation. I'm going to modify row 3. Row 3 will row 3 minus 2 times row 1. So I'm using this top pivot to get zeros below it. When I take row 3 minus 2 times row 1, I'm going to get 0, 0, then 1 minus 2 times 0, which is 1, and 2 minus 2 times 3, which is 6. I'll get negative 4 here. All right, so from here, we'll do a little bit of cleanup. I will just swap rows 3 and 2. So 0, 0, 1, negative 4 here, and put my row of all zeros at the bottom. All right, so now my matrix should be in row reduced echelon form. Next, I'm going to write the solutions to the system in parametric form. So now I basically take each row and write out the associated equation. So the first row says x1 plus 2x2 is equal to 3. The last row, or second row, says that x3 is equal to negative 4. And the last row tells me 0 is equal to 0. But because there's no pivot in the second column, I also know that x2 is a free variable, so I will add the equation x2 is equal to x2 because it's a free variable. From there, I will solve each equation for its leading variable here. x1 is equal to 3 minus 2x2. x2 is the free variable equal to x2. x3 is equal to negative 4. And lastly, I'll write my solution in parametric vector form. This is parametric form. Parametric vector form says create a vector. And in this case, all of my x1, x2, x3 have constants and x2 stuff. So I'll have a vector of constants plus a vector of x2 stuff here. So the constants are 3, 0, negative 4. The coefficients to x2 are negative 2, 1, and 0. So this would be my solution in parametric vector form. All right, going on to number 7. Determine whether or not the following sets of vectors are linearly independent or linearly dependent. So there might be some shortcuts that are available to me, but when in doubt, I could always put these into a matrix. I could always row reduce and see if there's a pivot in every column. So I'll look at the first one, A. I have a set of 3 vectors in here, and they all are in R3, so there's no immediate disqualifications here. I might look to see if any of the vectors are multiples of each other. Some quick way. I can't really see anything, so it looks like I'm going to do row reduction. So I'm going to take a matrix, and I'm going to put all my vectors in as columns of my matrix, and I'm going to do my row reduction on this. I will do row 3 minus row 1. Row 1 stays the same. Row 2 stays the same. Row 3 becomes 1 minus 1 is 0. 1 minus 2 is negative 1. 0 minus negative 2 is positive 2. From here I can see that row 3 minus 1/2 row 2 is going to give me a row of all zeros. So if I wrote that out, I would have 0, 0, 0 here. And what I see is that I'm in REF form. I have a pivot here, I have a pivot here. I don't have a pivot in third column. That means that the vectors are linearly dependent. Apparently that last vector is just a linear combination of the other two vectors. Now I might not be able to see exactly what the linear combination is. I actually could figure out if I finish the row reduction, but at this point I just need to know whether they're independent or dependent. Here they're dependent. And then I'll look at the next one. The next one I can take a little bit of a shortcut. I only have two vectors. So while for part A, it's hard for me to see if one of the vectors is a linear combination of the other two. If I only have two vectors, I can just check to see if they're multiples of each other. These ones are not multiples, so they are linearly independent. All right. And of course, just as a quick reminder, if I didn't remember that rule, I could always put them into a matrix and do row reduction. I would see that there's a pivot in every column. All right, number 8, find a linear combination of the vectors that yield this other vector. All right, so finding a linear combination means finding some number times the first vector plus some other number times the second vector that will somehow yield to this last vector. So if I can solve this vector equation, I will have found a linear combination of these vectors that yield the last vector. So all this is really saying is solve the vector equation. How do I solve that? I generate the augmented matrix and I do my row reduction. So my augmented matrix is going to look like this. And I'll do my row reduction. I'll do row 2 plus 2 times row 1. First row stays the same. Second row becomes negative 2 plus 2 times 1 is 0. 4 plus 2 times 3 is 10. Negative 1 plus 6 is 5. And then I will also do row 3 minus row 1. I will get 0. Negative 1 minus 3 is negative 4. 1 minus 3 is negative 2. Then we'll do 1/10 times row 2. We'll get 1, 3, 3, 0, 1, 1/2. And then maybe I'll just scale this one as well. I'm going to take negative 1/4 times row 3. I'll get 0, 1, and 1/2 here as well. From there, I will take row 3 minus row 2. First row stays the same. Second row stays the same. Last row becomes all zeros. Looks like I have one more row operation to do. This is going to be row 1 minus 3 times row 2. I got third row stays the same. Second row stays the same. And first row becomes 0, and 3 minus 3 times 1/2. So that is 3 minus 3 halves is going to be 3 halves. So I got 3 halves here. Now what that tells me, if I write out my solutions, it would tell me that x1 would equal 3 halves and x2 would equal 1/2. So is there a linear combination? There is. It turns out that 3 halves times the first vector plus 1/2 times the second vector should equal the third vector. All right, so that would be kind of the statement that it is a linear combination. I'm actually showing what the linear combination is. And the nice thing about putting in that form is I really should be able to check my work when I'm done as well, just by adding them together. All right. Next, number 9, let T be the transformation that is shown. And there's a bunch of questions about the transformation. So what is the domain? Well, I'm plugging in lists of 2 numbers into my transformation. That tells me my transformation is taking vectors from R2 and mapping them to 1, 2, 3, 4, R4, because my output is a list of 4 numbers. That means the domain is R2 and the codomain is R4. I am mapping vectors from R2 to R4. Then it says find a matrix that implements the mapping. Now I certainly could plug in 1, 0 and plug in 0, 1 to find the columns of A. But maybe the quicker version would be to say, I'm really thinking about this as plugging in that vector, and the output really looks like x1 plus 4x2 2x2, x1 minus 3x2, and x2. And I can maybe rewrite this as 1, 4, 0, 2, 1, negative 3, 0, 1 times x1, x2. So this is my matrix that does the transformation. Next says, is the transformation one-to-one onto both or neither? Well, I can answer that question by finding the pivots of the matrix A. So I'm going to do my row reduction on the matrix A. So I will take my matrix and maybe look at a little bit of row reduction. I'm going to do row 3 minus row 1. I will get the first two rows being the same. I'll get 1 minus 1 is 0, negative 3 minus 4 is negative 7, and then lastly I have 0, 1 here. Now I'm not going to show all my steps, but basically what I'm going to do is I'm going to take the second row and divide it by 2. That's going to put a 1 in that position. And I'm going to use that 1 to get zeros below it. I'm going to take row 3 plus 7 times row 2. I'm going to take row 4 plus the result for row 2. And so it's kind of easy for me to see that I'm going to be able to get those zeros below there. So once I'm at this stage, I can see that I have a pivot in every column, but not a pivot in every row. That tells me that transformation is one-to-one, but not onto. Okay, it's one-to-one. There's a pivot in every column. That tells me it's one-to-one. It tells me the columns are linearly independent. It tells me that solutions are unique, that there's at most one solution. It's not onto, because there's not a pivot in every row. That tells me that these two vectors do not span R4. It tells me there will not always be at least one solution. Okay, that's all the different vocab there. What is the image of the vector 1, 2 under the transformation? There's kind of two ways I could do this now. I really could just plug in 1, 2 into my transformation expression. And now that I have the matrix that does the transformation, I could certainly just take my matrix and multiply it by 1, 2, that input. If I do that multiplication, I'm going to get 1 plus 8 is 9, 0 plus 4, 1 minus 6 is negative 5, and 0 plus 2. So it looks like that is the image of 1, 2 under the transformation. And then lastly, is this vector in the range of the transformation? Well, the range is all the images. So is there some input, like an input like this, that would bring me to 1, 0, 2, 0, right? Is there some x that I can transform that will bring me to that vector? That's basically saying solve the matrix equation, right? So to solve the matrix equation, I will just write my matrix like this, and I will augment. And I will augment with that vector 1, 0, 2, 0. And I'll do my row reduction. So I'm going to take row 3 minus row 1. I got 1, 4, 1. Second row stays the same. Third row becomes 0. Negative 3 minus 4 is negative 7. 2 minus 1 is 1. And last row stays the same here. All right, so then I'm going to take 1/2 row 2. I have this. And I'm going to take row 3 plus 7 times row 2. And I'm going to get 0, 0, and then 1 plus 7 times 0 is 1. And at that point, I can really stop. I could certainly do one more operation to get a row of all zeros down here. But if I'm identifying the pivots now, I see there is a pivot in the far right column of the augmented column. That means there's no solution to the matrix equation. That tells me the vector is not in the range. All right. All right, as we continue on here, we get to number 10, solve the matrix equation AX equals B, or here this is A and this is B, and write your solution in parametric vector form. So I'm just going to take my augmented matrix and do my row reduction. Now one thing to note as I'm going through this is that a lot of these questions are being solved the same way, augmented matrix row reduction. The idea is you probably won't have all these questions on the exam. whether it's solve the matrix equation, solve the vector equation, solve the linear system, is this vector in the span? All those questions are essentially the same thing, just rephrasing. You'll probably get one of those questions, not all of those questions. In this case, I'm going to do my row reduction to find my solution and write it in parametric vector form, though. So I'm going to take row 2 minus row 1. And when I do that, I'm going to get 1 minus 1 is 0, 1 minus 0 is 1, 3 minus 3 is 0, 1 minus 1 is 0. So it looks like one nice row operation, and I'm already in RREF. As I look at that, I see there's no pivot in the far right column, so there are solutions. I see that x3 is going to be a free variable. So my first row tells me x1. I'm going to do a little shortcut here, is 1 minus 3x2. The equation is 1 plus 3x3. The equation is 1 plus 3x3 equals 1. I'm just subtracting the 3x3 to the other side right away. And then I see the next row tells me x2 is equal to 0, and I know x3 is a free variable, so I'll write that. Now I want to write my solution in parametric vector form. So I see that each of my components has constant stuff and x3 stuff. So my vector will have constant stuff, 1, 0, 0, and x3 stuff. Coefficients of x3 are negative 3, 0, and 1. That would be my solution in parametric vector form. All right, moving on to question 11 here. Simplify the expressions involving the invertible n by n matrices A, B, and C using the appropriate matrix properties. All right, so I have to use the appropriate matrix properties here. All right, so there might not be a clear way to start these. We just have to try and simplify it. So I'm going to use a couple properties that I know. I know that if I have AB inverse, the property says that the inverse of a product is the product of the inverses, but in the reverse order, right? So that means I can simplify this expression to be B inverse and then A transpose inverse. Now another property I have says that the transpose of the product is the product of the transposes, also in reverse order. Right? That means I can simplify this last expression to be A transpose B transpose. So that's my first layer of simplification. But now what I see here is the inverse of the transpose times the transpose. Right? So if I have any matrix, whether it's the transpose or not, just some matrix, if I multiply it by its inverse, the result will be identity. So that would simplify to the identity matrix. Identity times any matrix is just the matrix, so this is just B times B inverse. Actually, let's just save myself a little step here. B times B inverse is also identity. Identity times B transpose is B transpose. And lastly, identity times B transpose is B transpose. So that big expression simplifies to this. Now please note that even though this is the correct answer, there are many incorrect ways to get there. Right? So it's not uncommon for me to see a student who writes down the expression like this. They improperly, 100% incorrectly, distribute both the transpose and the inverse, which is not acceptable. And then they simply cancel terms like this, which is also not acceptable because multiplication is not commutative, but coincidentally for this problem, it comes out to the right answer. Right? There is no credit for this improper calculations, no credit for that, right? That is no good, okay? So make sure that you're using the properties and showing the properties that you're using when you simplify this stuff. Okay. All right, we go on to the next one here. All right, same thing here. Now, we in this case, I'm going to take apply the inverse property, so I'll have C and then C inverse times the quantity A plus B inverse. So that is not a product, that is A plus B quantity inverse times A plus B. And I've seen people try to distribute this inverse, but that is something we cannot do. The inverse of a sum, or the sum of two matrices, is not necessarily invertible, and so we can't necessarily distribute that inverse. But I know that C times C inverse is identity. If this is the inverse of AB times AB, that should also be identity, and the final result would be identity in this case. That's using the properties to simplify the expressions. All right, next, problem 12. Here's a matrix, so I want to solve the matrix x equals b, but I want to calculate the inverse of the matrix and use the inverse to solve this. So I have a 3 by 3 matrix. To calculate the inverse of a 3 by 3 matrix, I need to take my matrix and I need to augment the matrix with the identity matrix. So I'm augmenting not with just some vector b, but augmenting with the entire identity matrix, and then I'm going to do the row reduction. All right, so row operations here. I'm going to take row 2 minus row 1. First row stays the same. Second row becomes 1 minus 1 is 0, 1 minus 0 is 1, 3 minus 3 is 0, 0 minus 1 is negative 1, 1 minus 0 is 1, and I get 0 over here. So I'm really doing the row operation all the way across the full augmented matrix. Next, I'm going to take row 3 minus 2 times row 1. Here I'm going to get 0, 0, 7 minus 6 is 1, 0 minus 2 is negative 2, 0 minus 0 is 0, and 1 minus 2 times 0 is 1. So I have one more row operation to do. Right, I've gotten my pivots. I have zeros below them. I need to get zeros above them. I'm going to take row 1 minus 3 times row 3. In this case, row 3 will be the same. Row 2 will be the same. My new row 3 will be 1, 0, 0. Then 1 minus 3 times negative 2. That's 1 plus 6, which is 7. And 0 minus 3 times 0, and 1 minus 3 times 1 is minus 3. So after my row reduction, I have identity on the left, and the value on the right should be my inverse. So I believe a inverse should be 7, 0, negative 3, negative 1, 1, 0, negative 2, 0, 1. Now, if this is me on the exam, what I would like to do is just kind of check my work. And so to do that, I'm just going to take my inverse, and I'm going to multiply it by a, and I'm going to hope that I get to identity. So I'm going to take that guy, I'm going to multiply them together real quick. This is just a work check, right? This is just a work check. So when I'm doing this guy, I'll have 7 minus 6 up here. I will have, let's see, 1 plus 1 here. I will have 2, negative 2, plus 2 here. Then I go on to the second column, which is going to be 0, 1, 0. The last one's going to be 21 minus 21. It's going to be negative 3 plus 3. And it's going to be negative 6 plus 7. And when I simplify that, I'm going to get 1, 0, question. What's this guy right here? That should be negative 1 times 1. So that is 0. Good. Then 0, 0, 1, 0. 0, 0, 1. So I do get to identity. Now I certainly should or could also check to make sure that A times A inverse, the other order, also works, but I really don't need to do that. Just doing this quick check makes me feel a lot better that I haven't made any silly mistakes while calculating my inverse. So that's just kind of a work check to maybe be thrown onto a piece of scratch paper somewhere. So we'll clean that up now, deleting that stuff. So we've calculated our inverse. Next, we need to use it to solve the equation, right? So the idea is if we have ax equals b, and we now know the inverse, we could multiply both sides by the inverse. We know this guy would end up to be identity, and we know identity times x is just x. So this really represents our solution. So to find the solution, x, all I have to do is take my inverse and multiply it by b and see what the product is. So when I do this multiplication, I'm going to get 7 minus 6. I'm going to get 1, negative 1 minus 1. And I'm going to get negative 2 plus 2. Looks like I will get the answer. That is 1, negative 2, and 0. And that should be my solution. All right, so I've calculated the inverse, and I've used it to solve the matrix equation x equals b. All right, cruising right along, we're going to get to some of our application problems. So this is a network problem. So the figure to the right shows a freeway network where the flow rates are in cars per minute. Find the general traffic patterns in the network flow. So the idea is I have 4 nodes here, node A, B, C, and D. And for each of those nodes, the flow in should match the flow out. So for node A, I simply see what's incoming and what's outgoing. It looks like what's incoming to node A is x1. And what's outgoing is 40, x3, and x4. So x1 must equal 40 plus x3 plus x4. Then I look to node B. At node B, I have 200 coming in, and that should be equal to what's going out, which is x1 plus x2. At node C, I have x3 and x2 coming in, so x2 plus x3 coming in. And it looks like outgoing I have 100 and x5. So outgoing is 100 plus x5. Last node is node D. And at node D I have x4 and x5 incoming. And it looks like outgoing is just 60. Right, so by writing the equations related to each node, I am generating a system of linear equations. So from here, I'm going to want to clean this up just a little bit. So now I will say x1 minus x3 minus x4 equals 40. I will say x1 plus x2 equals 200. I will say x2 plus x3 minus x5 is equal to 100. And x4 plus x5 is equal to 60. All right, so now I have a linear system and I want to solve it. So I will generate the augmented matrix and do my row reduction. So in this case, my augmented matrix will look like 1, 0, negative 1, negative 1, 0, right, because I have 5 variables here. And it's going to be augmented with 40. Then I'll have 1, 1, 0, 0, 0, 200. I will have 0, 1, 1, 0, negative 1, and 100. And I will have 0, 0, 0, 1, 1, and 60. All right, so that is my augmented matrix. And now I have to do my row reduction. So I'll do my row reduction. I'm going to take row 2 minus row 1. Row 1 is going to stay the same. Row 2 is going to become 0, 1, 1, 1, 0, and 160. Then I will write down row 3 and row 4 as they will be unchanged. Then I'm going to do the next row operation, which will be row 3 minus row 2. This problem is really just bookkeeping here once we get to this stage, doing the row reduction. Row 1 and 2 stay the same. Row 3 becomes 0, 0, negative 1, negative 1, and then 100 minus 160 is minus 60. And then we'll go to the last one. All right. So from here I can also see that, so from here we will take row 4 plus row 3. And when I'm done with that, I'm actually going to multiply row 3 by negative 1 to clear those negative signs. So that means that we'll have that for row 1. Row 2 will be this. Our new row 3 will be 1, 1, and positive 60. And row 4 will be all zeros. Okay. A couple more row operations now. Almost done. We're going to take row 2 minus row 3. So row 4 will stay the same. Row 3 will stay the same. Row 2 will become 0, -1, 100. We're going to take row 1 plus row 3. Our new row 1 will be, 0 here, 1 here, and 100 here. So row 1 plus row 3 looks like that. Perfect. All right. And so from here, we have an RREF form, and we can write out our associated equations now. So if I'm taking my kind of shortcut method here, I'm going to say x1 is equal to 100 plus x3 minus x5 as I add and subtract the x3 and x5 to the other side of the equation. My x2 is going to equal 100 minus x3 plus x5. My x3 is a free variable. I can tell that because there's no pivot in the third column. My third row tells me that x4 is equal to 60 minus x5. And there's no pivot in the last column, so x5 will also be a free variable. So this would represent my solutions in parametric form. And then the question is, when x4 is 0, what is the minimum value of x1? All right, so it looks like this question really doesn't make a whole lot of sense here. So either there's an error in my work or there's an error in the network. I'm going to talk through the process here anyway. A better question for looking at this specific outcome would be, what is the maximum value of x5? That might be one type of question we can ask. And since all our flows must be positive, it looks like because x4 would have to be positive, x5 couldn't be greater than 60. So that might be a typical type of question for after we get done working through our network flow. So the important thing is that we use each node to generate an equation. Once we have our equations, we reorganize our equations to a linear system, and from there it's just row reduction and writing out our solutions to solve network problems. All right, we will move on to the next application. This is our chemical equations problem. So here we have a unbalanced chemical equation. We know how much of each molecule it would take to balance this chemical equation. And so we're going to use this vector representation for each of the molecules. And so looking at that, if we write out the associated vector equation, we would say some number of this first molecule, so that'd be some number times the molecule that is 3, because there's 3 atoms of sodium phosphate. And then we have 1 atom of phosphorus, and we have 4 oxygen, we have no barium, and no nitrogen. So that represents that first molecule. Then we have some number of the second molecule, which is 1 here, 2 here, 6 oxygen, 0, and 0. So that is the vector that represents that second molecule. Now this should be equal to x3 times our next molecule. This guy is going to be 0, 2, 8, 3, and 0, plus x4 times our vector representing our last molecule, which is 1, 0, 3, 0, 1. All right, I think I have all those correct. The only things to maybe watch out for are if we're looking at this guy, right? So that's really 2 atoms of nitrogen and 6 atoms of oxygen combined there. Right. So here I have my, have taken my general chemical unbalanced equation, and I've written the associated vector equation. Now from here, I could set up the homogeneous vector equation by subtracting these 2 guys to the other side. And then to solve that homogeneous equation, I would generate the augmented matrix and do my row reduction. So the associated augmented matrix would be 3, 0, 0, negative 1, because I'm subtracting this to the other side, augmented with 0. Then I would have 1, 0, negative 2, 0, 0, 4, 6, negative 8, negative 3, 0, 0, 1, negative 3, 0, 0, 0, 2, 0, negative 1, 0, right? So this would be my augmented matrix that I want to do my row reduction on. And there's lots of ways we can do this row reduction. I could certainly take that first row and divide by 3. The only problem was that would give me some kind of ugly fractions over here. I could certainly do that. That's totally fine. What I'm going to do instead is I'm going to switch the first 2 rows though. So I'm going to rewrite this as 1, 0, negative 2, 0, 3, 0, 0, negative 1, 0, 4, 6, negative 8, negative 3, 0, and so on and so forth. Okay, so now I'm going to carry on with my row reduction. I'm going to do row 2 minus 3 times row 1. First row is going to stay the same. Second row is going to become 0, 0, positive 6, negative 1, 0. Then I'm going to do row 3 minus 4 times row 1. I should get 0. I'll get 6 minus 4 times 0, which is 6. I will get negative 8 minus 4 times negative 2. That's going to be 0. And negative 3 and 0. And then my last 2 rows will be the same. All right, from here, I'm going to try to shortcut my process a little bit by looking for some patterns. And so what I see is if I'm looking at row 3 and row 5, they're just multiples of each other. Right? So I have 6, 0, negative 3 versus 2, 0, negative 1. I see those are multiples of each other, so that means I know that I could do a row operation to eliminate that last row. Right? So I could do row 5 minus 1/3 times row 3. So I don't necessarily need to go through all those steps, but knowing that helps me shortcut my row reduction process a little bit, right? Because I know that those two are just multiples of each other, so I can eliminate that one. Next, what I'm going to do is I'm going to move row 4 up into the second position because I want to use that as my pivot. So my first row is going to stay the same. My second row is going to become this guy. Then I'm going to move this row 3 where it was at. And then lastly, I have 0, 0, 6, negative 1, 0. So just kind of a rearrangement of the rows to help with my row reduction. Now at this point, I'm going to take row 3 minus 6 times row 2. 1, 0, negative 2, 0, 0, 0, 1, negative 3, 0, 0, 0, 0. 0 minus 6 times negative 3 is positive 18. And then I'll have negative 3 and 0. And 0, 0, 6, negative 1, 0, and 0, 0, 0, 0, and 0. And what I can see here now is that if I were to take row 4 minus 1/3 row 3, I would also get a row of all zeros. Now I can see that row 3 and row 4 are multiples, so I am going to use row 3 to eliminate row 4. Row 1 and 2 are going to stay the same. Row 4 is going to be all zeros. Row 5 is going to be all zeros. And then I'm also going to multiply 1/18 times row 3. This will give me 0, 0, 1, negative 1/6, and 0. All right, so now I'm in REF form. I see that I have one free variable. I see there's no pivot in the far right column, so there are solutions, there are infinite many solutions. Those are good checks at this point to make sure we're doing this process right. So now I have to do the back substitution. So I'm going to take row 2 plus 3 times row 3. So now I basically have a row of all zeros at the bottom, another row of all zeros. I have 0, 0, 1, negative 1/6, and 0. I'm going to have 0, 1, 0, and then 0 plus 3 times negative 1/6, so that's going to be negative 1/2, and 0. And I'll do one more row operation. I'm going to do row 1 plus 2 times row 3. This will be 1, 0, 0, and then 0 plus 2 times negative 1/6, which will be negative 1/3, 0. From here, I can write out my solutions. x1 is equal to 1/3 x4, x2 is equal to 1/2 x4, x3 is equal to 1/6 x4, and x4 is my free variable. And then I'm going to choose a value of 6 for x4, which is the smallest integer that will generate all integer values for my x1s, and I'll use those values to balance my chemical equation. So if x is 4, x1 is 2, I'll need 2 of the first molecule. If x4 is 6, x2 is going to be 3. I'll need 3 of the next molecule. And that should be equivalent to, give myself a little bit of room here. And that should be equivalent to, if x4 is 6, x3 is 1. So 1 times this molecule. And lastly, x4 is 6, so it'll be plus 6 of the last molecule. All right, and that would be the balanced chemical equation. Now, it's certainly fair game to have this type of question on the exam. However, you can imagine the row reduction will probably be a little bit kinder for the exam questions. We won't want to spend the whole exam time doing row reduction. All right. Number 15, let V be the set of all 2 by 2 diagonal matrices. All right, so this is the V is the set of all 2 by 2 diagonal matrices, and this is a basis for that space. So they're telling us this is a basis for that space. Answer the following questions. First one is, what is the dimension of V? Well, the dimension of a vector space is the number of vectors in its basis. In this case, there are 2 vectors in its basis. We have first vector, second vector in the basis. The dimension is 2. They're not asking for the dimension of the matrices, the dimension of the vector space. Is this vector in the vector space? It is if we can build it with our basis vectors. So what they're saying is that is this vector, which is the matrix 4, 0, 0, 3, a linear combination of the basis vectors? So let's see if we can kind of figure that out. Now, because we're dealing in more of an abstract space, we can't answer this question just by row reduction, so we just kind of got to look at it and see what's going on. Now, what I can see is that to get a value of 4 here, I'm going to have 2 of the first basis vector. Now, if I have 2 of the first basis vector, that's going to give me 2 in that final component. I have 3 in the final component over here, so I'm going to need 1 of the second basis vector. 2 times the first basis vector plus 1 of the second basis vector is going to bring me to the matrix 4, 0, 0, 3. That means that yes, that matrix, that vector, is in the vector space. And then it says, what are the coordinates of that vector? The coordinates are the number of each basis vector we need to build x. So in this case, I would represent that as the vector 2, 1. Those would be the coordinates of this vector according to this basis. All right, final question. Given this matrix, which row reduces to this following expression? So we don't have to do row reduction here. Answering the following questions about the null space and column space. The null space is a subspace of R what? So the null space are the solutions to AX equals 0, right? So they are the x's we can plug in that map to 0. So it's a subset of the x's, right? It's a subset of the domain. Here, if I were to take A and just multiply by vectors, the x's would have to live in R3. So the null space will be a subspace of R3. The null space is a subset of the domain, a subspace of the domain. Next, we want to find a basis for the null space. Well, to find a basis, I just solve AX equals 0. Now, to solve AX equals 0, all I would have to do is row reduce my matrix. But if I augment with zeros and do my row reduction, I'll just get this row reduced version over here with that extra augmented column. So from there, I can just write out my solutions. x1 is equal to negative x2. x2 looks like it's my free variable. And x3 is equal to 0. That means my solutions in parametric vector form would look like x2 times negative 1, 1, 0. So I can build any solution to AX equals 0 as multiples of this one vector. That one vector is a basis for my null space. Next, what's the dimension of the null space? There's only one vector in its basis, so the dimension is 1. Next, it says the column space is a subspace of our what? Well, the column space is the span of the columns of A. It's all the linear combinations of the columns. Each one of these columns lives in R4. If I take linear combinations, the result will also live in R4. The column space is a subspace of the codomain. So in this case, R4. Next it says find the basis for the column space. Well, if the columns span the column space, I know I can build the entire column space with the columns. To be a basis, they have to both span the space and be linearly independent. So I need to find the linearly independent columns. Looking at the row-reduced version of the matrix, I see there's a pivot in the first and third columns. That tells me that the first and third columns are linearly independent. So I will use those as my basis for the column space. So I will simply write in the first and third columns. And what is the dimension of the column space? There are 2 vectors in this basis, so the dimensions would be 2. And one final check, I should note that the dimension of the null space plus the dimension of the column space add up to 3, and there are 3 columns in my original matrix. That's a little trick, a little check that will always happen if we've done it correctly. All right, that wraps up this video. Once again, it's a long video, so hopefully you can just use it to watch specific pieces to get your questions answered. Thank you.